Every time you gaze up at the stars, you're not just seeing points of light, you're peering straight into the past, that flicker from a distant galaxy. It might have begun its journey to your eyes before Earth even existed. Light doesn't just illuminate the universe, it carries stories of exploding stars, colliding galaxies, and echoes from the dawn of time itself. Today, we're unlocking those cosmic messages. We'll follow light's incredible journey across space and time to reveal how scientists use it like a celestial detective, piecing together the history of everything from the death of a single star to the birth of the universe. And by the time we're done, you'll never look at a starry night the same way again, because the light reaching us now, it's not just showing us where things are, it's showing us what they were. Think of light like a cosmic postcard. Each beam traveling across the universe is stamped with clues about where it's been and what it's seen. When astronomers catch these faint signals, they aren't just measuring brightness, they're decoding fingerprints. Take starlight, for example. Pass it through a prism and it fractures into a rainbow, but look closer and you'll spot dark lines slicing through those colors like barcodes. Those gaps, they're caused by elements in the star's atmosphere gobbling up specific wavelengths, leaving behind a unique chemical signature. It's how we know a star like Betelgeuse is simmering with calcium and titanium, or that the gas giants orbiting other suns are rich in methane. And because light takes time to travel, that shimmer from Sirius, it left there 8 years ago, the glow of Andromeda, 2.5 million years in transit. Telescopes don't just magnify distant objects, they open windows into different eras, letting us piece together the universe's sprawling timeline, one photon at a time. The most powerful time machines we have aren't sci-fi devices, they're telescopes. Unlike any other tool, they catch photons that have been barreling through the vacuum of space since before dinosaurs roamed Earth. The iconic Hubble Space Telescope, orbiting far above our atmosphere's distortions, has glimpsed galaxies so distant their light set out when the universe was a mere toddler, just 5% of its current age. But Hubble isn't alone in this cosmic archaeology. Massive ground-based telescopes like Chile's ALMA array detect faint radio whispers from starburst galaxies, while instruments like the James Webb Space Telescope peer through infrared eyes, revealing nurseries where the first stars flickered to life. What makes these observatories so extraordinary isn't just their size, it's how they see the unseen. Every wavelength of light tells a different chapter of the universe's story. Ultraviolet reveals newborn stars scorching their birth clouds. X-rays expose matter spiraling into black holes, and radio waves trace the chilled gas between galaxies. By stitching together these fragments of ancient light, astronomers assemble a timeline stretching back over 13 billion years. And the farther we look, the stranger the cosmos becomes. Galaxies clump differently, stars burn hotter, and the very rules of physics seem to shift. Each telescope is like a single page torn from a history book, and scientists are patiently assembling them into a saga written in light. But how do we know the universe began with a bang? The answer is written in the sky, not in stars, but in a faint, ghostly glow that fills every corner of space. This is the cosmic microwave background, the afterglow of creation itself. Picture the universe in its earliest moments, a searing, dense soup of particles and energy. Then, about 380,000 years after the Big Bang, it cooled enough for light to break free. That first flash has been stretching across the cosmos ever since, diluted by expansion until it reaches us as a whisper of microwaves. In 1965, two radio astronomers named Arno Penzias and Robert Wilson stumbled upon this signal while troubleshooting a noisy antenna. What they first dismissed as pigeon interference turned out to be the oldest light ever detected, a direct echo from the universe's infancy. Today, satellites like Planck have mapped this glow with staggering precision, revealing temperature variations no larger than 100,000th of a degree. Those tiny ripples, they're the blueprints for everything the gravitational seeds that grew into galaxies, clusters, and the vast cosmic web we see today. The CMB is more than a relic, it's a Rosetta Stone for cosmology. Its patterns tell us how much of the universe is dark matter, how fast space is stretching, even hints of bizarre physics in the first trillionth of a second after the Big Bang. And because this light has traveled nearly 14 billion years to reach us, studying it is like finding a perfectly preserved fossil, one that lets us touch the dawn of time. Ever noticed how an ambulance siren sounds lower-pitched as it speeds away? That shift in tone is similar to what happens to light across the cosmos, just on a far grander scale. When a galaxy races away from us, its light stretches like a cosmic rubber band, sliding toward the red end of the spectrum. We call this redshift, and it's not just a curiosity, it's proof the universe itself is stretching, carrying galaxies along like raisins in an expanding loaf of bread. Edwin Hubble made this revolutionary discovery in the 1920s. By measuring the redshift of distant galaxies, he noticed something astonishing. The farther away a galaxy was, the faster it seemed to be receding. This wasn't just random motion, it revealed the fabric of space was growing, pushing galaxies apart. The implications were staggering. If you could rewind this expansion, everything would crunch together to a single, unimaginably dense point, the moment we now call the Big Bang. Today, redshift is one of astronomy's most vital tools. It acts like a cosmic speedometer, telling us not just how fast a galaxy is moving, but also how far away it is. The most distant objects we've spotted, faint galaxies flickering at the edge of observable space, have their light stretched so dramatically it arrives as faint infrared whispers. Without redshift, we'd have no way to map the universe's structure or measure its expansion rate. And that expansion isn't just steady, it's accelerating, driven by a mysterious force we still don't fully understand. But redshift isn't only about distance, it also changes how we see celestial objects. A galaxy whose light took 10 billion years to reach us appears redder and dimmer than it truly is, like a faded photograph from the distant past. That's why telescopes like James Webb are designed to capture infrared light. It lets us see these redshifted galaxies as they were in their youth, long before our solar system even existed. So next time you hear a siren fade into the distance, think bigger. That same physics, writ large across the cosmos, is how we've traced the story of everything, from the birth of space to the fate of galaxies. And speaking of cosmic fate, some of the best clues come from the explosive deaths of stars. Nothing in the universe announces its own death with quite such spectacular brilliance as a supernova. When a massive star exhausts its fuel and collapses, it unleashes an explosion so fierce it can outshine entire galaxies, briefly radiating more light than 1 billion suns. But these cataclysmic events aren't just fireworks, they're cosmic mile markers, helping astronomers map the vast distances of the universe. The most valuable of these stellar explosions are called Type Ia supernova. Unlike their unpredictable counterparts, these detonations follow a strict script. They occur in binary star systems where a dense white dwarf siphons material from its companion until it hits a critical mass, then boom. Because the detonation always happens at the same threshold, these blasts reach nearly identical peak brightness, making them perfect cosmic measuring sticks. Here's how it works. Imagine you have two identical light bulbs, one close, one far. The farther bulb looks dimmer, right? Supernova work the same way. By comparing how bright a type Ia appears from Earth to its known true brightness, astronomers can calculate its distance with stunning precision. In the late 1990s, teams using these stellar lighthouses made a jaw-dropping discovery. Distant supernovae were fainter than expected, meaning the universe wasn't just expanding, it was accelerating. Something invisible, dubbed dark energy, was pushing space apart faster and faster. But supernovae don't just measure the present cosmos, their light carries echoes of earlier epochs. The oldest detected so far erupted when the universe was just 3 billion years old, offering snapshots of a younger, more violent cosmos. Telescopes like Hubble and James Webb now hunt these explosions in galaxies so remote their light has traveled most of cosmic history to reach us. Each supernova is a time capsule, its spectral fingerprints encoding details about the star's composition, the interstellar medium it passed through, and even the expansion rate of space at the moment it exploded. And as we collect more of them, they reveal not just where we are in the universe, but where everything is going. At the very edge of observable space, cosmic lighthouses blaze with unimaginable ferocity quasars. These aren't just brilliant objects, they're runaway black holes feasting on entire galaxies, vomiting out energy so intense it outshines 1,000 Milky Ways combined. Born when the universe was barely a tenth of its current age, quasars are more than distant spectacles. They are forensic floodlights, casting illumination across billions of light years to expose the hidden scaffolding of creation. The secret behind their brilliance lies in their monstrous hearts, supermassive black holes, some weighing billions of suns. As gas, dust, and stars spiral toward these gravitational pits, friction heats the material to millions of degrees, creating disks so bright they can be seen clear across the cosmos. But what makes quasars priceless to astronomers isn't just their energy, it's how they transform into cosmic backlights. When their radiation passes through vast clouds of hydrogen or threads of dark matter on its journey to Earth, specific wavelengths get absorbed, leaving behind a barcode of dark lines in the spectrum. These absorption lines are gold mines. Like reading fingerprints at a crime scene, scientists decode them to map the distribution of matter between galaxies, revealing the cosmic web, the sprawling network of gas and dark matter that weaves the universe together. Some quasars are so old, their light has traveled over 12 billion years to reach us, meaning we're seeing them as they were when galaxies were still clumping into their first structures. And here's where it gets even wilder. Occasionally, a quasar's light doesn't travel straight, it gets warped by the gravity of massive galaxy clusters along its path, bending around them like a cosmic magnifying glass. This phenomenon, called gravitational lensing, can split a single quasar's image into multiple arcs or rings, revealing details otherwise too faint to detect. But that's a story for our next revelation. Einstein saw something extraordinary about gravity. It doesn't just pull objects together, it bends the very fabric of space-time itself. And because light follows this warped geometry, massive objects like galaxies can act like cosmic magnifying glasses, twisting and amplifying the glow of distant stars behind them. This phenomenon, gravitational lensing, isn't just a quirk of physics. It's nature's ultimate telescope, letting us peer deeper into the universe than any human-made instrument ever could. Take Hubble's famous image of galaxy cluster Able 1689. At first glance, It looks like a swarm of golden galaxies, but look closer, and you'll spot delicate blue arcs streaking around them like celestial brushstrokes. Those aren't part of the cluster. They're distorted images of galaxies billions of light years farther away, stretched and mirrored by the cluster's immense gravity. Without lensing, those ancient galaxies would be far too faint to detect, but the real magic happens when lensing reveals the invisible. See, galaxy clusters contain far more mass than their visible stars, and gas can account for. Most of it is dark matter, the mysterious substance that outweighs ordinary matter 5 to 1. By studying how lensing bends light around these clusters, astronomers can map dark matter's hidden structure, tracing its ghostly gravitational fingerprints across the cosmos. Sometimes, the effect is even more dramatic. When a distant quasar aligns perfectly behind a massive foreground galaxy, its light fans out into a glowing ring, an Einstein ring, a perfect cosmic bullseye predicted by relativity. Other times, a single background star, briefly magnified by a passing foreground object, flares up like a cosmic flashbulb, allowing us to spot planets drifting between stars. Gravitational lensing isn't just about seeing farther, it's about seeing differently. It turns the universe into a hall of mirrors where distortions reveal truths too subtle for direct observation. And as telescopes grow sharper, this natural trick of gravity keeps uncovering wonders, newborn galaxies from the cosmic dawn, the faintest whispers of the first stars, and clues to the dark matter web that binds it all together. Now, imagine if we could read the life story of a star just by its light. From fiery birth to explosive death, every phase leaves a luminous signature, a celestial memoir written in photons. And that's exactly what astronomers do. The glow of every star is like a celestial autobiography, each wavelength revealing chapters written in atomic fire. Take newborn stars blazing within nebulae like Orion. Their intense blue light betrays youth and ferocity, with surface temperatures scorching over 20,000 degrees. Run your fingers along their spectral lines, and you'll find hydrogen and helium signatures so strong they dominate the cosmic palette. But stars age just as we do. Over billions of years, nuclear fusion transforms their cores, altering the very light they emit. A star like Betelgeuse, bloated and crimson, whispers of its late-stage fusion through spectral traces of carbon and oxygen, ash left behind by eons of stellar combustion. Spectroscopy doesn't just reveal a star's past, it unveils its companions too. When an exoplanet tugs its host star during orbit, the subtle wobble imprints itself on starlight as rhythmic Doppler shifts. Other times, distant worlds announce their presence by dimming their stars' glow as they transit, leaving atmospheric fingerprints in the filtered light. That's how we've sniffed out water vapor on alien worlds and detected organic molecules swirling in faraway systems, each discovery tucked inside starlight's intricate code. Even a star's death leaves luminous clues. The violent expulsion of a supernova seeds space with heavy elements, from the iron in your blood to the calcium in your bones. Catch the light from these explosions, and you'll spot spectral lines screaming with silicon, neon, and gold elements forged in a star's final, defiant moments. Some stellar corpses, like white dwarfs, glow with a stripped-down spectrum, their outer layers gone, leaving bare carbon-oxygen cores cooling into cosmic embers. This interplay of light and matter isn't just academic. It's how we've mapped the Milky Way's spiral arms, dated ancient star clusters, and even predicted the sun's eventual fate. Every photon carries evidence of its origins, etched by the physics of fusion, gravity, and time. And as telescopes grow sharper, starlight stories grow richer, revealing not just how stars live and die, but how their lives intertwine with our own existence. Yet for all we've decoded, the universe holds darker mysteries, ones that don't glow at all. Invisible threads of dark matter weave through space, bending starlight in ways that betray their presence. The universe holds its greatest secrets in the dark. Not the black of empty space, but something far stranger, an invisible scaffolding that sculpts galaxies, twists light, and outweighs ordinary matter 5 to 1. We call it dark matter, and though it refuses to glow, its fingerprints are everywhere. Look at any galaxy spinning like a cosmic carousel, and you'll spot the telltale signs. The outer stars whiz around so fast they should fling into the void, yet something unseen grips them in place. That something is dark matter, an enigmatic substance whose gravity weaves the universe's largest structures while remaining utterly transparent to light. So how do you map the unseeable? Astrophysicists have a clever trick. They let light do the detective work. When distant starlight passes through a region dense with dark matter, the invisible mass bends its path like a lens, subtly distorting the galaxy's shape. This effect, called weak gravitational lensing, transforms entire galaxy clusters into cosmic magnifying glasses. By measuring how these background galaxies appear stretched and twisted, scientists trace dark matter's hidden geography in stunning detail. The resulting maps reveal sprawling filaments and voids, a vast cosmic web where dark matter forms the skeleton, and galaxies cling like dewdrops on a spider's silk. Supercomputer simulations bring this shadow architecture to life. Run the universe's evolution in reverse, and you'll watch dark matter clump first, pulling gas and stars into its gravitational embrace. Without it, galaxies would never have formed in the early universe's soupy chaos. Yet for all its dominance, dark matter remains stubbornly elusive. Is it a sea of undiscovered particles? A quirk of gravity we don't yet understand. Every flicker of bent starlight brings us closer to answers, but for now, the universe keeps its greatest architect hidden in plain sight. Among the grand cosmic tapestry of stars and galaxies, something much smaller yet just as influential shapes our view of the universe: cosmic dust. These microscopic grains, no larger than a speck of smoke, drift between the stars, acting as both a cosmic curtain and an artist's brush. Starlight passing through these clouds doesn't just fade, it transforms. Dust scatters blue light more than red, giving distant stars and galaxies a reddish tint, like sunlight filtering through a smoky sky. In dense regions, dust becomes a total blindfold, blocking our view of stellar nurseries and galactic cores. But where dust hides, it also reveals. Infrared telescopes like the James Webb Space Telescope don't just see through these veils, they turn them into cosmic projector screens. Because dust absorbs starlight and re-emits it as heat, infrared cameras trace its glow, uncovering hidden factories where stars are born. The iconic pillars of creation, towering columns of gas and dust in the Eagle Nebula, appear dark in visible light but blaze brilliantly in infrared, exposing newborn stars carving their way out of dusty cocoons. There's poetry in how these tiny particles shape the universe. The same dust that obscures distant stars is also the raw material for planets and even life itself. Heavy elements forged in supernova and stellar winds condense into dust grains, which later clump together to form asteroids, comets, and ultimately, the building blocks of Earth-like worlds. When you breathe, some atoms in your lungs might once have drifted between the stars, wrapped in these cosmic dust motes, Yet dust is more than just a bystander in the universe's story. In galaxies like our Milky Way, dense dust lanes spiral between stars, shaping how we see their structure. And in the most distant galaxies, dust can fool astronomers into underestimating star formation rates until infrared eyes peel back the curtain. So while dust might seem like a nuisance, it's a vital player in the cosmic drama, hiding secrets in one moment and illuminating them in the next. But if dust whispers the universe's softer stories, there are other events that scream across the cosmos with unimaginable force in the darkest corners of space. Violence erupts on a scale that defies imagination. Gamma-ray bursts. These aren't just explosions, they're cosmic detonations so powerful they outshine entire galaxies for a fleeting moment. Packing more energy than our sun will produce in 10 billion years, they flash into existence and vanish before you could finish a sentence, leaving behind only an echo of light rippling across the cosmos. What could possibly unleash such fury? The leading suspects are collapsing supermassive stars, one so enormous their cores implode into black holes with enough force to punch twin jets of plasma through the star at nearly the speed of light. When those jets pierce the stellar surface, they unleash a concentrated beam of gamma rays, the universe's most energetic light. Another trigger could be the collision of neutron stars, city-sized remnants of dead suns so dense a single teaspoon would weigh 1 billion tons. As they spiral together in a final, catastrophic dance, they too can unleash a gamma-ray siren before vanishing into a black hole, but the real magic happens after the initial blast. As the jet plows through surrounding gas, it creates a glowing aftermath, an afterglow visible for days in X-rays, radio waves, and visible light. This lingering fingerprint allows astronomers to track GRBs back to their host galaxies, revealing they often occur in regions bursting with newborn stars. That's a crucial clue. These explosions prefer stellar nurseries, where short-lived supermassive stars are born. What makes GRBs truly invaluable is their reach. Their light slices through vast stretches of cosmic gas largely untouched, letting astronomers study the composition of material between galaxies. Some bursts detected today erupted when the universe was less than 1 billion years old, making them probes of the earliest cosmic epochs. We're essentially catching the last whispers of stars that died before Earth even existed. And here's the spine-tingling part. If one of these beams pointed directly at Earth from within our galaxy, the radiation could strip away our ozone layer, triggering mass extinctions. Fortunately, GRBs are rare and the universe is vast, but their existence reminds us of the raw, untamed forces shaping the cosmos, forces that flicker briefly, yet illuminate the darkest chapters of the universe's story. Now, imagine a celestial object that doesn't just explode, it spins, beaming light like a cosmic lighthouse with precision rivaling atomic clocks. That's the realm of pulsars. Some of the most precise timekeepers in the universe aren't man-made. They're city-sized stars spinning faster than a kitchen blender. Pulsars are the lighthouses of the cosmos, born when massive stars collapse into neutron stars, so dense that a sugar cube-sized chunk would weigh as much as Mount Everest. As these remnants spin, their magnetic fields funnel intense beams of radiation into space. From Earth, we catch these beams as rapid, clockwork pulses, some flickering hundreds of times per second with a regularity that rivals atomic clocks. This precision turns pulsars into cosmic laboratories. When two pulsars orbit each other, their dance creates subtle distortions in spacetime, exactly as Einstein's general relativity predicts. By tracking tiny changes in their pulse timing, Scientists have confirmed gravitational waves exist long before detectors on Earth could catch them. One famous pair, discovered in the 1970s, has spiraled closer by nearly 4 meters per year, a perfect match for Einstein's equations and a discovery that earned its observers a Nobel Prize. But pulsars don't just test relativity, they've rewritten the rules of planet hunting too. In the early 1990s, astronomers noticed strange hiccups in the pulses of a star called PSRB 1257+12. The culprit, 3 rocky worlds circling the pulsar, the first exoplanets ever confirmed. These weren't just any planets. They were survivors, likely forged from the ashes of a shattered solar system after the star's violent collapse. What makes pulsars truly remarkable is their versatility. Some, like the millisecond pulsars in globular clusters, spin so fast their surfaces move at a quarter the speed of light. Others serve as galactic GPS arrays of these flashing beacons, could one day help spacecraft navigate interstellar space. And when gravitational waves ripple past a pulsar, they stretch spacetime just enough to delay its pulses by microseconds, turning a network of these stars into a galaxy-scale wave detector. From probing the nature of gravity to uncovering unlikely planets, pulsars prove that even the universe's most extreme objects can become tools if we learn to read their light. And speaking of extremes, nothing bends the rules of physics quite like the ultimate cosmic trapdoors, black holes. At the heart of every galaxy lies the universe's ultimate paradox, a place where gravity wins its fiercest battle against light. Black holes don't just swallow stars, they twist spacetime into knots so tight that photons, the fastest travelers in existence, vanish without escape. Yet, ironically, it's the absence of light that makes these cosmic monsters visible. When superheated gas spirals toward a black hole's event horizon, friction heats it to millions of degrees, creating an accretion disk so bright it outshines entire galaxies. That's how we first glimpsed the unseeable in 2019. The Event Horizon Telescope's historic image revealed a fiery ring of light, framing the dark abyss of M87's supermassive black hole. The physics here is poetry in motion. As matter hurtles toward the event horizon at nearly light speed, photons get caught in a gravitational dance, some flung outward in blazing jets, others bent into impossible paths by the black hole's spin. The result, a shadow where light seems to disappear, a perfect silhouette against the glowing disk. This isn't just an optical illusion, it's a direct window into Einstein's equations. The size and shape of that shadow confirm predictions about the black hole's mass and rotation, proving space-time really does warp like a trampoline under extreme gravity. But black holes don't just consume light, they rewrite its rules. Take gravitational lensing around a black hole, where background starlight gets stretched into surreal arcs, or the eerie photon sphere, a region where light orbits the black hole like a trapped firefly before either escaping or plunging inward. Even time distorts near these beasts. A clock ticking at the edge of an accretion disk would run noticeably slower than one on Earth, a phenomenon called time dilation, etched into the very light we observe. What makes these discoveries revolutionary isn't just their strangeness, it's how they transform darkness into a tool. By studying light's struggle near black holes, we've verified relativity's wildest predictions, mapped the invisible fabric of spacetime, and even glimpsed the limits of physics itself. And as telescopes grow sharper, these cosmic vacuum cleaners may yet reveal the deepest secrets of gravity, where the universe's rulebook bends until it breaks. Now, let's turn from the darkest corners of space to the star that brings us light every day, our sun. Unlike black holes, The sun doesn't hide its secrets in shadow. It broadcasts them in a steady stream of photons, each carrying clues about the forces churning beneath its surface. The sun isn't just the bright orb in our sky, it's the only star close enough to reveal its secrets in exquisite detail. Every beam of sunlight carries encoded messages about the inferno at its core, where temperatures reach 15 million degrees and hydrogen atoms collide with such force they merge into helium. This process, nuclear fusion, is the engine powering nearly all stars, but here, just 8 light minutes away, we can observe it in action. Solar telescopes dissect sunlight like cosmic forensic scientists, peeling back layers to expose the chaos beneath. Sunspots, darker and cooler patches on the surface, betray tangled magnetic fields. Solar flares erupt with the energy of 1 billion atomic bombs, while coronal mass ejections hurl charged particles across the solar system, events that, when directed at Earth, can knock out satellites and trigger auroras. But sunlight's revelations go deeper than storms on a star. When astronomers first split sunlight into a spectrum, they found something extraordinary, a mysterious yellow line no known element on Earth could explain. They named the culprit helium, after the Greek sun god Helios, marking the first time an element was discovered in space before it was found on our planet. Today, the sun's spectrum remains a Rosetta Stone for stellar physics. Absorption lines reveal not just its composition, hydrogen, helium, traces of iron and calcium, but also its rotation, temperature, and even the supersonic winds howling off its surface. What makes our sun so invaluable is how it bridges the cosmic and the familiar. Its light lets us test theories about star formation, magnetic fields, and plasma physics up close, knowledge we then apply to distant stars we'll never visit. Solar observatories like NAS, a Parker solar probe, dive through the sun's corona, enduring scorching heat to measure how energy ripples through its atmosphere. Meanwhile, telescopes tracking sunquakes, ripples on the solar surface allow us to peer inside, much like geologists use earthquakes to map Earth's interior. Yet for all its brilliance, the sun is just one of countless stars, many with planets of their own, and when those worlds pass in front of their suns, they leave subtle fingerprints in starlight. Imagine standing under a street lamp at night, watching moths flutter around the light. Now picture that same scene across interstellar distances, a star glowing steadily, with planets silently circling in the darkness. Most of these distant worlds are too faint to see directly, but astronomers have a brilliant workaround. They watch for the subtle ways planets betray their presence by tampering with starlight. The most prolific planet hunting technique, the transit method, works like a cosmic dimmer switch. When an exoplanet passes in front of its star, it blocks a minuscule fraction of the light. For a star like our Sun, an Earth-sized planet causes a dip of just 80 parts per million, like spotting a flea crawling across a spotlight. But instruments like NAS, a Kepler space telescope, are so sensitive they can detect this flutter. Over 4,000 exoplanets have been discovered this way, each transit revealing the planet's size, orbit, and even hints about its atmosphere as starlight filters through any gases present. Then there's the wobble method. A star with orbiting planets doesn't sit perfectly still. It dances slightly as gravity tugs it back and forth. This motion imprints a telltale signature on the star's light, compressing its wavelengths as it moves toward us and stretching them as it recedes. By tracking these subtle color shifts, astronomers can calculate a planet's mass and orbital distance. Hot Jupiter's giant planets hugging their stars were first caught this way, their HEFTY Chinese letter pulling hard enough to make their stars sway like buoys in a cosmic tide. But the real magic happens when starlight becomes a chemical sniffer. When the James Webb Space Telescope observes a transiting exoplanet, it doesn't just measure the dip in brightness, it dissects the light that skims through the planet's atmosphere. Molecules in that alien air absorb specific wavelengths, leaving dark lines in the spectrum. Already, JWST has spotted water vapor on scorching gas giants, carbon dioxide in hazy skies, and even potential biosignatures like methane and oxygen in Earth-sized worlds' atmospheres. Every flicker of starlight holds clues. A sudden brightness spike might reveal a volcanic exomoon in orbit. An oddly skewed transit could hint at Saturn-like rings. Even the reflected glow of a planet, its phase curve, can map temperature variations between a world's scorching dayside and frigid night. What began as a search for shadows has blossomed into a field where light doesn't just reveal planets. It lets us study their weather, seasons, and potential to harbor life. Yet among these discoveries, one question looms: could any of these distant worlds be signaling us on purpose? The answer might lie in the next frontier, not just reading light, but decoding intentional messages woven into it. For centuries, humans have wondered if we're alone in the cosmos, but what if the answer has been traveling toward us all along, encoded in beams of light? The search for extraterrestrial intelligence, or SETI, isn't just about listening for radio waves. It's about scanning the heavens for artificial light signals, deliberate flashes or patterns that nature could never produce. Imagine a civilization on a distant planet aiming a powerful laser our way, pulsing it in a mathematical sequence. To our telescopes, it might look like a single star suddenly blinking in perfect rhythm, like Morse code written across the galaxy. This isn't science fiction. Projects like Breakthrough Listen use some of Earth's most sensitive telescopes to hunt for these optical and infrared laser signals. The logic is simple. Light travels faster and with less interference than radio waves over cosmic distances. A focused laser beam could carry a message millions of light years with pinpoint precision. Already, astronomers have caught tantalizing candidates' brief bursts of light that defied natural explanation, though none have yet been confirmed as alien in origin. But lasers aren't the only clue. Some scientists search for megastructures' hypothetical alien engineering on a staggering scale. Picture a civilization so advanced it builds a Dyson swarm, a vast array of solar collectors encircling its star to harness energy. From afar, such a structure would dim the star's light in unnatural ways, perhaps flickering in geometric patterns as the megastructure rotates. Telescopes like Kepler have actually spotted stars with bizarre, irregular dimming, like the infamous Tabby's star, though dust clouds or comets remain more likely explanations than alien construction crews. The beauty of this search lies in its simplicity. Whether it's a pulsed laser or a shadow cast by alien engineering, light becomes the universal language, a carrier wave for intelligence across the void. And while we haven't found definitive proof yet, the mere possibility transforms every glimmer in the night sky into a potential hello from a distant neighbor. Long before SETI, humans were already using light to decode the cosmos, just in a far more ancient way. Thousands of years before satellites and spectrometers, our ancestors gazed skyward with nothing but their eyes and saw patterns in the chaos. Ancient astronomers from Babylon to Mesoamerica didn't just watch the stars, they mapped them with astonishing precision. The Babylonians etched eclipse records on clay tablets as early as 750 BCE, noting how lunar shadows crept across the Earth like clockwork. Greek philosophers tracked Venus's wandering path, realizing it wasn't a star at all, but a world dancing around the sun. And high in the Yucatan jungle, Maya scribes calculated the cycles of Venus to within minutes over centuries, aligning their temples with celestial events. What's truly breathtaking is how they transformed simple observations into cosmic clocks. Take the Antikythera mechanism, a corroded bronze device salvaged from a 2,000-year-old shipwreck. When scientists peered inside using modern imaging, they found gears and dials intricately modeling the moon's phases and predicting eclipses. This wasn't just a calendar, it was a mechanical universe in miniature, proof that ancient Greeks had grasped celestial mechanics long before Newton. But perhaps the most haunting records come from China. In 1054 CE, court astronomers scribbled an urgent note about a guest star flaring near Taurus, so bright it cast shadows for weeks. Today, we know they witnessed the Crab Nebula's violent birth, a supernova whose remnants still glow in X-rays. Without telescopes or spectra, these early observers mapped time itself using nothing but patient eyes and etched stones, turning the sky into humanity's first science lab. Their legacy isn't just historical trivia, it's the foundation that lets us decode the universe's deepest secrets today. Now, armed with technology they couldn't have imagined, we're building on their vision. The frontier of cosmic discovery keeps expanding, not just because we're looking farther, but because our eyes on the sky have grown exponentially sharper. Imagine a telescope mirror so vast it could cradle an Olympic swimming pool, or a space observatory sensitive enough to detect the heat signature of a bumblebee on the moon. This isn't science fiction, it's the reality of modern observatories, where engineering marvels are rewriting the rules of what light can reveal. Take the James Webb Space Telescope, floating 1,000,000 miles from Earth. Unlike Hubble's mirror polished to perfection, Webb's golden segmented surface acts like a giant cosmic honeycomb, catching infrared whispers from the universe's first galaxies. Because these ancient objects are racing away from us, their light stretches into invisible infrared wavelengths like a cosmic Doppler effect. Webb doesn't just see this light, it dissects it with microshutters thinner than a human hair, allowing it to study hundreds of distant galaxies simultaneously. Already, it's spotted galaxies so mature they shouldn't exist in the early universe, appending our timeline of cosmic evolution. But the revolution isn't just in space. On Earth, telescopes like Chile's forthcoming extremely large telescope are turning mountains into time machines, with a mirror spanning 39 meters wide enough to fit a blue whale lengthwise. It will collect more light in one night than all the photons that have ever entered the human eye. What makes it truly groundbreaking is adaptive optics, a system that counteracts atmospheric blurring in real time, using laser-guide stars' artificial beacons created by exciting sodium atoms high in the atmosphere. These systems adjust their mirrors thousands of times per second, sharpening images to rival space telescopes. Then there's the magic of interferometry, where multiple telescopes act as one. By combining light from arrays like the Atacama Large Millimeter Array, astronomers achieve resolution so fine they could spot a baseball on the moon. This technique has let us photograph the swirling gas around supermassive black holes and trace the faint glow of planetary nurseries light years across. The result, we're not just observing the cosmos, we're reverse engineering its history. Each photon captured by these instruments carries timestamps from different epochs, letting us assemble a cosmic family album that stretches from the first flickers after the Big Bang to the birth of planets around neighboring stars. And with next-generation tools on the horizon like gravitational wave detectors tuned to space-time ripples or quantum-linked telescopes, we're poised to see farther, clearer, and deeper into light's encrypted chronicle of the universe. While our current telescopes have already revolutionized how we see the cosmos, the next generation of instruments is poised to rewrite the rulebook entirely. Take the Nancy Grace Roman Space Telescope, launching later this decade, a cosmic surveyor designed to capture panoramas of the universe 100 times wider than Hubble's deepest images. But Roman isn't just about breadth. Its hypersensitive infrared eyes will hunt for the fingerprints of dark energy by mapping how galaxies warp starlight across billions of years, unraveling why the universe's expansion keeps accelerating. And then there's LISA, the Laser Interferometer Space Antenna, a trio of spacecraft that will float millions of miles apart, linked by lasers to catch gravitational waves from colliding supermassive black holes, ripples in space. I'm so subtle they stretch light itself like a cosmic accordion. But the real game changer might be how we process the flood of data these missions generate. Artificial intelligence is already sifting through telescope archives, spotting patterns no human could, like identifying rare gravitational lenses or predicting supernova before they flare. Combine that with quantum optics, where entangled photons could one day let telescopes peer through interstellar dust with unprecedented clarity, and suddenly, the universe's faintest whispers become audible. We're not just building better cameras, we're crafting entirely new ways to decode light's hidden narratives. Yet for all these technological leaps, the most profound shift might be philosophical. Every time we extend our vision farther into space or deeper into light's quantum fabric, we're forced to reconsider our place in the cosmos. Are we merely observers of this grand story, or participants in a universe that seems increasingly aware of its own reflection? The answers won't just come from bigger telescopes, but from the way we choose to interpret the light they gather, connecting the dots between photons, time, and the very nature of reality itself. There's a quiet profundity in realizing that the same light reaching our eyes tonight has traveled across epochs, brushing past galaxies and black holes long before human history began. Astronomy does more than catalog distant objects. It stitches together a story where we're both witnesses and participants. When we analyze the redshift of a quasar or the spectrum of a supernova, we're not just collecting data, we're deciphering pages from a cosmic autobiography that began with the Big Bang. This search for understanding transcends science. It's woven into art, mythology, and philosophy. Ancient cultures worshipped the sun as a deity. Renaissance painters chased its golden light to capture divine radiance on canvas. Today, our tools are telescopes and spectrometers, but the impulse remains the same: to find our place in a narrative vaster than ourselves. The Hubble Deep Field image, for instance, isn't merely a snapshot of galaxies. It's a mirror reflecting how small, yet how remarkably curious we are. Those faint smudges of light represent countless worlds, each with its own untold stories, and here we are, a species on a pale blue dot, piecing together their secrets. Yet misconceptions linger. Some imagine starlight as a static snapshot, frozen in time, but it's more like a message in a bottle, weathered by its journey. Others assume brighter stars are closer, when in fact, a dazzling star might simply be a titanic furnace burning fiercely in the void. And while popular media often depicts space as a riot of color, most cosmic objects emit light our eyes can't perceive until instruments translate them into visible hues. These nuances matter because they shape how we interpret the universe, not as a static backdrop, but as a dynamic, evolving tapestry where light is both messenger and timekeeper. What makes this journey extraordinary is how it reshapes perspective. To study cosmic light is to confront scales so vast they humble, and details so precise they astonish. It's a reminder that curiosity, whether through a philosopher's telescope or a child's first glimpse of the Milky Way, is what binds us to the stars, and in that light, both literal and metaphorical, we find something timeless, the urge to look up and wonder. Some of the most persistent cosmic myths sound poetic: twin stars sharing a single soul, light arriving instantaneously from across the universe. But peel back the romance, and you'll find science even more wondrous. Take the idea that we can see the Big Bang, the truth. We don't observe the explosion itself, but its afterglow, the cosmic microwave background, a cooled remnant from when the universe became transparent. That faint static on old TVs, a fraction of it traces back to this primal light, stretched by expansion into microwaves over 13 billion years. Another common mix-up involves starlight's speed. While it's fast enough to circle Earth 7 times in a second, space is so vast that even nearby stars' light takes years to reach us. Sirius's glow. A snapshot from 8 years ago, the Andromeda Galaxy, a 2.5 million year old postcard. This delay means every glance at the night sky is a mosaic of different epochs, not a real-time display. Then there's the myth of twin stars appearing identical to the naked eye. In reality, most stellar pairs differ in age, composition, or distance. They just happen to align from our viewpoint. True binary systems, like Sirius and its faint white dwarf companion, often look nothing alike. Even the color contrast between stars, like the fiery orange of Betelgeuse versus the icy blue of Rigel, reflects their surface temperatures, not mystical bonds. Perhaps the most tempting misconception is that light travels unscathed across the cosmos. In truth, photons brave a gauntlet of obstacles. Interstellar dust reddens them, magnetic fields twist their paths, and expanding space stretches their energy. What finally reaches our telescopes is a transformed messenger, bearing scars from its epic journey. Dispelling these myths doesn't diminish the universe's magic, it sharpens our awe. Understanding light's limits helps us grasp its true power, not as a flawless mirror, but as a storyteller whose tales grow richer with every correction. And in that refined view, we find something far more compelling than fiction, the unfiltered wonder of how the cosmos actually works. The universe has been writing its autobiography in light since the dawn of time, and we've only just begun learning how to read it. Every discovery we've made, from deciphering starlight's chemical fingerprints to catching echoes of the Big Bang, reveals how deeply light shapes our understanding of existence itself. Those shimmering points in the night sky, they're not just distant objects, they're chapters in an epic story where the very fabric of reality bends to light's journey. What makes this exploration so extraordinary is how it connects us across time. When you watch sunlight dance on water, you're interacting with photons that spent 8 minutes racing from a nuclear furnace 93 million miles away. Glimpse the Andromeda Galaxy, and your eyes catch light older than humanity itself. Even the radio static between stations carries whispers from the universe's infancy. Light doesn't just illuminate, it bridges epochs, linking our fleeting moment to cosmic events older than Earth. But here's the thrilling part, we're not passive observers. With every telescope we build, every spectrum we analyze, we're adding new sentences to this grand cosmic narrative. The James Webb Space Telescope peers back to the first galaxies, while gravitational wave detectors listen for spacetime's ripples, tools that let us read between the lines of light's ancient script. And as technology evolves, so does our ability to decode even subtler messages. from the atmospheres of exoplanets to the invisible pull of dark matter. So the next time you step outside under a starry sky, take a moment to marvel at the miracle unfolding above you. Those beams of light traveled unfathomable distances through eons of cosmic history just to reach your eyes. They're invitations to wonder, to question, to keep exploring, because the universe isn't just out there, it's speaking to us, photon by photon, in a language we're finally learning to understand. If this journey through cosmic light has sparked your curiosity, don't let it end here. Hit that like button if you enjoyed the ride. Subscribe to join us on more deep dives into space's greatest mysteries, and drop a comment below. Tell us which cosmic revelation blew your mind the most. Until next time, keep looking up. The universe still has countless stories left to tell, and they're all written in light.